Hello, everybody. Welcome back to Markov Processes. In today's video, we're going to talk about what is one of my favorite things to talk about in discrete time, discrete state space Markov processes. And that is the idea of a first step analysis, which allows us to do kind of complicated computations and really take advantage of that Markov property, that idea of once you've taken a step or two steps or three steps, no one cares where you came from, only where you are. And so I think you're really going to like this, but first I have to get a couple of miscellaneous items out of the way. So let me share my screen and let's get going. Okay, so miscellaneous items, I'm just going to call this list a list of some things, some miscellaneous things, some random things, although random is a loaded word in this class. So the first thing is an alternate way to compute the expected value of a non-negative random variable. And there is an analog to this formula for continuous random variables, but because we're talking about discrete random variables right now, I am going to state it in that case. So suppose that X is a discrete non-negative integer valued random variable. That's pretty sloppy there. So it's taking values 0, 1, 2, 3 on up. I want to talk about the expected value or mean value for X. So hopefully you can recall from your probability prerequisite that expectation is a probability weighted average. And in this case, in the discrete case, when we're running over these values, I'm going to sum over all of those values, X times the probability that X equals X. So that's the usual way we compute expectation. But in this specific non-negative integer valued case, there's another way we can do this, and that is by summing tail probabilities. What do I mean by that? I mean, we're going to look at the sum as X goes from 0 to infinity of the probability that X is greater than X. Or equivalently, with a little re-indexing, this is the sum as X goes from 1 to infinity, the probability that X is greater than or equal to X. So those are the same thing. It's just a little re-indexing. So I'm going to focus on this one right here when we prove it. And this sort of expression is going to come up in some upcoming proofs. And then we're going to be able to say, hey, that's just an expectation and work from there. So let's prove this. Let me get rid of this guy over here. And to prove this, I'm going to start with the right-hand side, the sum as X goes from 0 to infinity, the probability that X is greater than X. Now, X is integer valued, non-negative integers in particular, but if I were to write out a few terms here, this is the probability that X is greater than 0, plus the probability that X is greater than 1, plus the probability that X is greater than 2, plus ... And let's consider this first probability right here that X is greater than 0. I can write that as the probability that X is 1, or I can add on the disjoint probability that X is 2 or X is 3, etc. And all of that just corresponds to this first term. So continuing, I'm going to write out the probability that X is greater than 1 by summing up a bunch of probabilities there as well. The next term, the probability that X is greater than 1, is the probability that X equals 2 plus the probability that X equals 3 plus the probability that X equals 4, etc. And now I'm going to add on this term, the probability that X is greater than 2. And that consists of the disjoint events that X is 3 or 4 or 5. And so we can add those probabilities. X equals 3 plus the probability that X equals 4 plus ... And then we have this continuation, another ... out here. So if you look at all these terms we've gathered, we have exactly one probability that X equals 1. And we have two probabilities that X equals 2. And we have 3 probabilities that x equals 3. And if we wrote out more, we would see that we have 4 probabilities that x equals 4 on up. So, sorry about that. This is equal to, and I'm going to leave a little space, the probability that x equals 1 plus 2 times the probability that x equals 2 plus 3 times the probability that x equals 3 plus ... And of course, I can put a 1 times in front of this guy. And I can also put in front a 0, because why not, times the probability that x equals 0. And when I write it like that, you can now see that we have the sum as x goes from 0 to infinity of x times the probability that x equals x. So we got that by summing up these tail probabilities, and what we have in the end is the more familiar definition of expectation. So expectation as a tail probability sum, and in the continuous setting, we can actually integrate some tail probabilities, and we'll do that when we start to get into continuous stuff. I will review that sort of thing then. So this is number 1 in our list of things that we're going to need. The second thing I'm going to put in this list, and the last thing, this is a pretty short list. Suppose that the random variables x1, x2, x3, etc. are independent and identically distributed. So most of you are probably familiar with calling these random variables IID. Then we can write the expected value of the sum as I goes from 1 to n of the xi as, so expectation is a linear operator, and that means we can take the sum inside to be a sum outside. And this is going to be equal to the sum as I goes from 1 to n, the expected value of xi. And I didn't use that the random variables were independent or identically distributed or anything like that. Now, if x1, x2, x3, etc. are identically distributed, that means that they are governed by the same PDF or PMF, probability density function or probability mass function. And so they have the same probability of taking on certain values and being in certain regions. And on average, they're going to be the same, even though individually they're not just, if you were to observe these, you're not going to see the same thing over and over again. But you have the same probability of being in the same place. And again, the same expectation, which means because these guys are identically distributed, I have the sum as I goes from 1 to n of the expected value of any one of these. I could write x5 here, but I'm going to write x1. So the I is gone, just x1. And that means that this sum is the expected value of x1 plus the expected value of x1 plus the expected value of x1 n times. And so this is equivalent to n times the expected value of x1. I did not use independence anywhere here, so I really don't even need it in this statement. I used the fact that they're identically distributed to say all the expectations are the same, and that was it. Now, this is not actually the thing in the list that I wanted to tell you about today. This is something that hopefully you've already seen. What we're going to use today is we're going to start again with the same assumption that we have some independent random variables that are identically distributed, and they don't have to be independent, but identically distributed is enough for what I'm saying here today. And I'm going to let capital N be a positive integer valued random variable. And we're going to look at the expected value of the sum as I goes from 1 to capital N of x sub I. So we are summing up a random number of random things. And if we were to guess that this was going to look something like this, you might think the answer, and don't write this down because this is going to be wrong, but you might think that the answer is n times the expected value of x1. Now, this can't be right because we've got a random quantity in here made up of lots of little random bits. And when we take the expectation, we're averaging out the randomness. So the answer should be non-random or constant. And yet what I've written has a random variable on the right-hand side. So that's not exactly right. But what would be right is, let me move this over a little bit. We're going to see that this is equal to the expected value of n times the expected value of x1 if, and this is only a sufficient condition, not a necessary condition, n is independent of the x's. Again, there might be other cases where you can write it this way. We are guaranteed that this is going to work if n is independent of the x's, and that's what we're going to show right now. And this is something known as Wald's identity or Wald's equation. So let's prove it. This time I'm going to start with the left-hand side. And as I was saying before, we have a whole lot of randomness in here. We've got n random, and then we're looking at x1, x2, x3, up to x sub n, a whole bunch of random variables. In fact, I think we have too much randomness here. So let's get some of it out by setting or fixing some of this. Let's condition on the value of n. N being a positive integer valued random variable, it's going to take values potentially from 1 to infinity. I'm going to get the expected value of this quantity. I goes from 1 to capital N of xi, conditional on n being a fixed value, little n, and we're going to multiply by the probability that n equals little n. So here we're computing this expectation by conditioning on the value of n. The next thing I'm going to do is use the fact that capital N equals little n, and I'm going to plug that in here. So now I have the sum as n goes from 1 to infinity of the expected value of the sum as I goes from 1 to little n, xi, given n equals n, times the probability that n equals n. So just because I've used up the information that capital N equals little n does not necessarily mean I'm done with this information, but it does here because I'm assuming that n is independent of the x's, x1, x2, x3 on up. So right now I've got some random stuff over here that does not depend on n, and some random stuff over here that does not depend on anything over here. And that means that the conditional expectation is the same as the unconditional expectation. In other words, I can drop this since n is independent of x1, x2, x3 on up. And this is just like, it's the same reason if you're looking at a joint probability that say x equals x given y equals y, if they're independent, then knowing that y equals y should tell me nothing about the probability that x equals x. And if they're independent, I should be able to completely drop the stuff after the conditional line. If you in fact write this out by definition as the intersection probability over the marginal probability that y equals y, and then use the more usual definition of independence to say that the probability of the intersection factors into the two different pieces, then you'll see that it does in fact hold using independence. And I in fact use this as a definition for independence rather than get this from the usual definition of independence. So okay, back to what we were computing. I do get to drop this guy over here by independence. And so I'm going to write this by independence. This is the sum as little n goes from 1 to infinity, the expected value of the sum as I goes from 1 to little n of xi times the probability that n equals n. And now I'm back to that same sum as before, and I'm going up to a fixed number, not a random number. And because they're identically distributed, I get the expected value of x1 plus the expected value of x2 plus the expected value of x3 up to xn. They're all the same expectation. So that expectation can be written as n times the expected value of just one of them. I could use x5, x7, any x there, times the probability that n equals n. So that was using the fact that the x's are identically distributed. Now that expectation doesn't involve n, so I'm going to pull that out. And what I'm left with is that sum of n times the probability that n equals n. That's how you compute the expected value of n. And this is what we wanted to show. So we started, sorry about that. We started with the expectation of a random sum or a sum of a random number of random variables. And if they were identically distributed, we can write it as the expected value of one of them times the expected value of the expected number of terms in the sum. And again, this is known as Wald's identity or Wald's equation. So with that, we're ready to state theorem pi 2. We have these pi theorems, and they all sort of go with the limiting or stationary distribution of a Markov chain, which in most cases are the same thing, not all the time. So theorem pi 1 said that if you have a Markov chain that's irreducible, aperiodic, and positive recurrent, if you start at any state I and run for a long time, if you look at the limit as n goes to infinity of the probability of going from I to j in n steps, that again, if you have irreducibility, aperiodicity, and positive recurrence, this will exist and be independent of I. So this is like a long run kind of probability of ending up in a state J, and you've gone for so long that the chain does not remember that it started at I. And we showed that any limiting distribution is stationary. And a stationary distribution is one such that, move all this over. If you were to do this over and over and over again, starting from I or starting from anywhere and collecting the output, there is some sort of shape of a distribution out here. And it is stationary in the sense that, you've reached those proportions in the limit. And again, this is from repeated sample paths. So regenerating things like this with different random input. But if you have settled down into this limit, then you should still be there at time infinity plus 1. So let me copy this. Oops. I got a lot more than I bargained for there. So I'm going to call that time infinity plus 1. And it is stationary in that sense. So if you start anywhere, you will end up at one point here, but do it repeatedly and collect the output, you'll get a picture, a histogram. And if you went one more time step, you'll see the same picture, and it's stationary in that sense. And remember, the stationary equations were pi j equals the sum over I of pi I pij. So the probability you're in state j, you can just sum over all possible states I, the probability you're in I, and then multiply that by the one-step transition probability of moving from I to j. So that was theorem pi 1. And theorem pi 2 is not going to be about a limiting distribution, which happens to be stationary, but just about a stationary distribution. So suppose that xn is an irreducible, that means all states communicate, Markov chain. And I'm a little too lazy to write it, but on a discrete state space and in discrete time. So here is the theorem. The Markov chain xn is positive recurrent if and only if a stationary distribution exists. And I have a little more to say here, but a limiting distribution does not always have to exist. If it does, it is stationary. If it doesn't, that doesn't mean you can't find a stationary distribution. It's just not something you settle down to in the limit. So if we have irreducibility and positive recurrence, and you'll notice that this theorem actually doesn't need a periodicity, then we have this if and only if statement here. Furthermore, so like in this case, if the chain is positive recurrent, the stationary distribution is unique and is given by, I'm going to write an expression for the stationary distribution in terms of the expected return time starting at a state to get back to the state. But before I do that, we've got some overlap already with theorem pi 2. This is theorem pi 2. We've got some overlap with theorem pi 1. We had irreducibility, positive recurrence, and aperiodicity, and that means that a limiting distribution exists. We then showed that a limiting distribution is stationary. Right now we're saying irreducible, positive recurrent is enough for a stationary distribution. That's not enough for a limiting distribution. But if you take our irreducibility and positive recurrence and also throw in aperiodicity, this theorem is still going to hold. And that means we're going to have a unique stationary distribution. And when you combine this with theorem pi 2, a limit exists, the limit is stationary, the stationary distribution is unique. And so they are one and the same. If someone asks you for a limiting distribution, you could choose to solve for it using the stationary equations. And vice versa. You could, if someone asks you for a stationary distribution, you could look at powers of the matrix and try to find a stationary distribution by looking at how the Markov chain is behaving at time infinity. So the expression, the stationary distribution, is given by pi I, the probability of being in state I, is 1 over the expected, starting from state I, time to return to state I. So here, this TI is the first return time, not the first hitting time. When we talk about hitting time, we do allow for hitting at time 0. But when we're trying to talk about a return time, we do have to take at least one step. So this is going to be the minimum over all n greater than or equal to 1, such that xn equals I. And this should feel maybe intuitively okay, because if you imagine starting a sample path of a Markov chain from anywhere, and let's look at a state I. So because the chain is irreducible, you will eventually hit I. And then, because the chain is positive recurrent, you'll eventually return to I. And now, using the Markov property, since you know you're at I, you don't care what happened before that. You're going to set off again on your travels, and you will eventually return to I. And you will eventually return again and again and again. And these little sojourns between I are not necessarily the same number of steps, but on average, they have this many steps in them, the expected return time to I starting from I. So if this was like the expected return time to state I starting from I was maybe 8 steps, then in the long run, the probability you're going to be at I, if you eventually hit it and then you keep coming back on average every 8 steps, then as you reach this, sort of equilibrium, once you eventually hit it and you come back on average every 8 steps, you expect to be there about 1/8 of the time. And that's what this is saying. The probability you're at state I in this example would be 1/8. So I think that this equation that's in the rectangle right now is a pretty feel-good equation, and I hope you feel the same. Because of the missed class on Monday, I'm not going to take the time to prove this. I'm going to write it up and or make a video that I'm going to have up before this weekend. It's going to be totally optional reading or viewing. It's going to be pretty, what is the word? Pretty, not going to be pretty. That's not the word. It's going to be a little bit tedious. And again, totally optional. You can totally succeed in this course without ever watching that or reading that. All right, we're going to use this result pretty soon, but the next thing I want to talk about is what I'm really excited to talk about today, and that is the idea of a first step analysis for Markov chains. So this is a whole kind of suite of computations And I'm just going to jump right in with some examples. So basically, someone, meaning me, is going to ask you to perform some computations that at first glance seem pretty complicated. I'll show you exactly what I mean in an example, but first let me set up a Markov chain. So I'm going to need quite a few states here just to illustrate certain things. So I'm going to make my state space be 1 through 5. And then I'm going to make up a transition matrix. So across the 1 row, I have 0.3, 0.2, 0, 0.1, and 0.4. Across the 2 row, I have 0, 0.1, 0.5, 0.1, and 0.3. Across the 3 row, I have 0.4, 0.4, 0, 0, 0.2. Across the 4 row, I have 0, 0, 0.7, 0.2, 0.1. And across the 5 row, I've got 0.6, 0.1, 0, 0.3, and 0. And you might want to pause the video and write this one down because I'm going to be referring to this matrix for the entire rest of today's lecture. And I'll try to keep copying and pasting it, but it might be helpful to you to have it right in front of you. I'll make this 0.4 look more like a 0.4. So I'm going to grab it so I have it for the next slide. And let's answer our first step analysis question. Question 1. I'm going to start the chain in state 2. And I want to find the expected number of steps for the chain to first hit state 1. Now, if you give this to your roommate who has had some probability, but not Markov chains, they are going to just start spinning around and making themselves crazy and going, well, I could go from state 2 directly to state 1, but I could go to state 2. I could go to state 2 again, and then maybe to 3 and 1. I could go from 2 to 5 and 5 to 1, or 2 to 5 to 4. And, it's just going to get ridiculous really fast. But you have the power of Markov chains and the idea of a first step analysis. So to do this, we're going to set up some notation. I'm going to let T be the first hitting time on state 1. Now, a hitting time usually starts from 0. So I'm going to define this to be the minimum over all n greater than or equal to 0, such that xn equals 1. I suppose if you define it starting from 1, you can do something similar to what we're about to do, but you would have to adjust some things. Now, what we want to compute is we want the expected time to hit state 1, given that we're starting at state 2. We're going to use the power of Markov chains and this kind of reset by the Markov property. We're going to say, where do we go? We're going to start at 2. Where do we go in 1 step? If we've hit 1, great. If not, where are we now? And we're going to kind of reset time and say, okay, let's start from there. Let's call that time 0. And so let me write that down. Now, because of this, we're going to be looking at many different starting values, not just a starting value of 2. So I'm going to define something right here. I'm going to call a variable, I'm going to use u. You can use whatever you want. I use u because it kind of looks like a mu and it kind of looks like an expectation. I'm going to let this be the expected time until we hit state 1, given we started at state I. And what we want to find is u2. And given how we define t to be the first hitting time, which can start from 0 on state 1, we know, for example, that u1, starting from 1, how long does it take you to the very first time you hit state 1? It takes 0 steps. So let's find u2 though. u2, what I'm about to do is kind of informal. I think it's nice and intuitive though. And when we're done, I'll go back and show you how to formalize this just a little bit more. So we're starting from state 2. We want to know how many steps it takes to get to state 1. I have to take at least one step because we're not there. So I get a 1 plus. Now I'm going to look at the 2 row of the matrix, and you'll notice that I can't go from 2 to 1. So the next option is to go from 2 to 2. So I'm going to say 1 plus. With probability 0.1, I go to 2. And now I have to start counting all over, starting from 2. So that's going to be the expected number of steps starting from 2 to hit state 1. And we call that U2. So I already have that 1 step counted. And then I've kind of reset time. So in a picture here, I've gone from 2 to 2, and I said, I haven't hit state 1. So I'm just going to say, okay, 1 step has gone by and time 0 was here, but now I'm going to call this time 0 and start over. And continuing looking at that 2 row of the matrix, which is now in the upper right corner, starting from 2, I can go to 3 with probability 0.5. And then I'm going to have to, starting from 3, count the expected number of steps to hit state 1. And we call that U3. And I can go from 2 to 4 with probability 0.1. And now I'm at 4, so I want to start there and count the number of steps starting from 4 to hit state 1, and that's U4. And finally, from 2, I can go to state 5 with probability 0.3. And then once I'm at 5, I want to start counting, starting from state 5, the number of steps to get to state 1. And again, I'm sort of zeroing out time there. I started at 2. I counted my 1 step. In case that 1 step took me to state 2, I went here. If it took me to 3, I went here. If it took me to 4, I went here. If it took me to 5, I went here. And in all of those cases, I sort of reset and started counting from time 0 again. You'll notice all of these U's are defined in terms of starting at time 0. Now, even though all I want to find is U2, U2 has been defined in terms of U3, U4, and U5, so I need to start setting up more equations. Let's go for U3 next. Starting from state 3, what is the expected time until we hit state 1? I have to take at least 1 step because I know I'm not there. I'm in state 3. And I'm going to look at the 3 row of the matrix. Now with probability 0.4, I go directly to state 1. So I'm going to put 0.4. With probability 0.4, I stop. There are 0 more steps. If you want this to look like the line above, then you put a U1 there, but we've already said, where did we say it? Here, we already said that U1 is 0. So if you'd like to put a U1 there so that the equations look the same, by all means, go for it. Starting at state 3 with probability 0.4, I also can move to state 2, and then I have to start counting over there. So with probability 0.4, I want the expected number of steps to hit state 1 starting from state 2. Now I already took 1 step to go from 3 to 2, and that was counted right here. Finally, looking at the 3 row, with probability 0.2, I have moved to state 5, and I have to start counting from state 5. So I'm going to add on a 0.2 times U5. Let's go for U4. Starting from 4, it takes at least 1 step to hit state 1. From 4, I can't go directly to 1. I can't go directly to 2. I do go to 3 with probability 0.7. So I'm going to add on 0.7 times U3, which is the expected number of steps now starting from state 3. This is the first step analysis. We take 1 step, and then if we're at 3, we start from there. If we're at 4, we start from there. And yeah, I can go from 4 to 4 with probability 0.2. And then I get U4, which is the expected number of steps to end at state 1, starting from state 4. And finally, with probability 0.1, I go to state 5 and start counting from there. So finally, I need a U5, and I'm going to run across that final row of the matrix. I'm at 5, and I want to hit 1. I need to take at least 1 step. Now with probability 0.6, I have moved to state 1, and I count 0 more steps, which again, you could write U1 because U1 is 0. With probability 0.1, I go from state 5 to state 2, and now I start counting from state 2, so I put a U2 there. And with probability 0.3, I go from state 5 to state 4, so I'm going to put a U4 right there. And we have a system of equations we need to solve in order to find U2. I think we're going to get a lot of other solutions for free when we do this. So you can solve this any way you want to for the purpose of this class. You could do back substitution. You can certainly use software like MATLAB or Mathematica. I think it's easiest to write this as a matrix vector system of equations. And on an exam, you will not have to solve a system like this. So you just have to figure out how to get through it for each homework problem. But I am going to write this as a matrix filled with coefficients multiplied by a vector U2, U3, U4, and U5. And I'm going to set that equal to. So what I'm about to do is to move everything here over to the left-hand side. And I'm going to leave these ones on the right-hand side, which means I'm going to make a vector over here with 1, 1, 1, and 1, and I'm going to start moving everything else to the left. So here I have a U2, and I'm going to subtract off 0.1 U2, which leaves me with the coefficient 0.9. The U3 coefficient is going to be this 0.5, but move to the other side, it's negative 0.5. The U4 coefficient moved to the left side is negative 0.1. And the U5 coefficient moved to the left side is negative 0.3. And so I'm just going to continue, and I'll see you back here in a second. So I have my matrix vector system of equations. If you call this A, then you can get the vector we want, U2, U3, U4, U5, by taking A inverse and multiplying on the right by the column vector 1, 1, 1, 1. And so I did that, and I got approximately, got a little rounding in here, 4.376, 3.308, 4.492, and 2.785. What we wanted was U2, so there's our final answer. If you start from state 2, it will on average take you 4.376 steps to hit state 1. And fractional steps are fine. It's an average, so it's like 2.5 children is fine, even though half a child is not so fine. We got the others for free because we were solving a system of equations, and you might want to look at some of these and look at the matrix and see if they kind of make sense to you. There's a lot going on in this matrix, so I'm not sure you'll always be able to do that. But you'll notice that U5 is quite small compared to the others. This is supposed to be the expected number of steps to reach state 1 starting from 5. If you go back to the matrix, which is really messy right now, get rid of all of this, you'll notice that when you start from state 5, you have quite a large, relatively speaking, quite a large probability of moving to state 1. And so you'll tend to move to state 1 faster than you would starting from other states. And that's why, for example, we saw that the average number of steps to hit state 1 starting from 5 was lower than it was in the other starting cases. So these equations, I think, felt good. I think they felt intuitive, but what are we really doing formally? Formally, we are computing the expected value of t, which is still the first time to hit state 1, given we're starting at state 2, and we're doing it by conditioning on where we are at time 1. So this is going to be the sum as I goes from 1 to 5 of the expected value of t, given x1 is I and x0 is 2, times the probability that x1 is I, given x0 is 2. Okay, so over here, I have transition probabilities. This is little p sub 2i. And here I have a bunch of expectations. And they're different depending on whether or not I is 1. So I'm just going to write out, notice I don't have an equal sign. This is not equal to the line above. I'm just looking at some of these expectations. First, in the case where I equals 1, t was the first hitting time on state 1. We start from 2 at time 0. We went to 1 at time 1. We know what t is. Given this information, this t is already determined. It is equal to 1. We hit state 1 for the first time in one step. So this is known. This is now fixed. It's like a constant given this information. So this is the expected value of 1 or 1. In the other cases, for all the other i's that are not equal to 1, when we compute the expected time to first hit state 1, given x1 is I, and we know that that's not 1, and x0 is 2, we want the expected number of steps to hit state 1. We know we've gone from state 2 to state I, and that I was not 1. So that is one step right there. And then we are now at state I. So I had a picture before. Let me draw that again. We're at state 2. And we've moved to state I. So we're going to count that one step. And then what was time 0, we're going to shift that over and kind of consider this time 0. So, I didn't mean to leave that there. That's not the end of that line. We take one step and then we have to add on the expected value of t given that x0 is I. We've sort of re-indexed time. I'm going to go put this stuff up into this equation up here. And what we have is that the expected value of t given x0 is 2 is equal to 1 times p to 1 plus 1 plus the expected value of t given x0 is 2 times p to 2 plus 1 plus the expected value of t given x0 is 3 times p to 3 plus 1. I say that like it's the last line. x0 is 4 times p to 4 plus 1 plus the expected value of t given x0 is 5 times p to 5. I am going to distribute out those p's, multiply by 1 and multiply by this. I'm going to do that with every term, and I'm going to collect those sort of leading p's. So I've got p to 1 from here plus p to 2 from here plus p to 3 from here plus p to 4 plus p to 5. And then I have the rest of the stuff, which is this expectation times p to 2. Now that expectation, we have a name for it, and it is u2. So this is u2 p to 2 plus this expectation, which is u3 times p to 3 plus u4 times p to 4 plus u5 times p to 5. And those probabilities that I have up here, that is summing across the second row of the probability transition matrix. From state 2, you have to go somewhere, even if it's back to state 2. So those sum up to 1. So we get 1 plus, and maybe I'm just going to switch these around when I write it. P to 2, U2 plus P to 3, U3 plus P to 4, U4 plus P to 5, U5. That's exactly what we had before. I mean, I actually used the numbers from the 2 row of the matrix, but this is exactly what we had before. And we got the 1 in a slightly different way. Before we were saying we have to take 1 step and then, but right now the 1 came from adding those probabilities, which I think is kind of a cool thing to notice that we got that in a slightly different way. But all of this was our equation for U2. We got to exactly what we got before, but now we did it by formally conditioning on where we went to at time 1. And we did it with a first step analysis. We said, where do I go in 1 step and then reset? I have another question for you that we can also answer by a first step analysis. Here's the setup. If the chain starts in state 2 and goes until it hits either state 1 or state 5, I want to know the probability that when we stop, so we're going to stop when we hit 1 or 5. I want to know the probability that when we stop, we're in state 1 as opposed to state 5. Let's set up notation. I'm going to let t be the first time, the first hitting time on states 1 or 5. So the minimum for n greater than or equal to 0, such that xn is 1 or xn is 5. What we want to find is the probability that the chain at time capital T is 1, given we started at state 2. And just like before, we're going to do a first step analysis. We're going to start at 2, we're going to go 1 step and reevaluate. And this means that we're going to need to change the starting value up. So we're going to define lowercase p sub I to be this probability starting in state I. Now what we want to find is P2. And we already know a couple of probabilities here. If the chain starts in state I and goes until it hits 1 or 5, what is the probability that it stops in state 1? So if we start in state 1, we're stopped instantly, and we stopped in state 1 with probability 1. So we know that P1 is 1. And if we start in state 5, we've hit that stopping rule and we've stopped instantly. And so the probability that when we stop, we're in state 1, that's not happening. We're stuck in 5. And so we know that the probability that we start at 5, we know that the probability given we start in 5, that when we stop this chain, and by the way, we stop when we hit 1 or 5, the probability we stop at 1 is 0 because we've stopped and we're at 5. We've stopped before we even started. So I'm going to do a first step analysis. I'm going to try to make an equation for P2, and then we're going to need a few more P's. Now this is a probability, and this is not a number of steps. So I'm not counting a number of steps until, and starting out by saying, okay, let's take 1 step and then see what happens. So there's no 1 plus here. But I am going to look at the 2 row. And with probability 0.1, I am going to move from 2 to 2, and then I'm just going to start from there trying to figure out where this chain is going to stop. So I get a 0.1 times P2 and a 0.5 going across that row times P3, a 0.1 times P4 plus a 0.3 times P5, which is 0, or right P5, either way. And again, there's no 1 plus because I'm not counting time steps in this first step analysis. And we could write this out formally. I'm not going to take the time to do that here. It's very similar to what we did before. We're conditioning on where we go in 1 time step. So to compute this, I need P3. Starting from state 3, if I'm going to go until I hit 1 or 5, what's the probability that when we stop observing this, when we reach the stopping rule, we're in state 1? So with probability 0.4, I hit state 1, and we end in state 1 with probability 1, which again, you could write as P1 because P1 is 1. Still going across that 3 row with probability 0.4, I go to state 2, and now starting from state 2, I want the probability that's starting from 2 and ending at 1 or 5. I want the probability that we end at 1 versus 5. And finally, with probability 0.2, I go from state 3 to state 5. And now what is the probability? If we're going to stop when we hit 1 or 5, what's the probability we stopped at 1? That probability is 0 because we've already hit state 5. And we're going to need one more. P4. So looking at the 4 row with probability 0.7, we go to state 3, and now I want the probability starting from state 3. With probability 0.2, we go to state 4. So now I want the probability starting from 4. And with probability 0.1, we go from 4 to 5, and it's over. The probability we have ended at 1 is 0 because we have ended at 5. So I have a system of 3 equations here. You can solve them in a similar way. I set up a little matrix system of equations, and I got that P2 is approximately 0.353. P3 is approximately 0.541, and P4 is approximately 0.474. These numbers should not add up to 1 because the subscripts here mean this is where we started, this is where we started, this is where we started. These are kind of different universe probabilities. You know, you're going to go until you hit 1 or 5. What's the probability that when you stop, you're at 1? And one of them means you started at 2. In a different scenario, you started at 3. And in a different scenario, you started at 4. So these are all different universe probabilities, and they should not add up to 1. But we wanted this, so our final answer is 0.353. Let's do another first step analysis. So far, our first question, we started at a state and we computed the expected number of steps to hit another state. The second question, we defined a stopping rule. We started at a state and said we were going to stop if we hit this state or this state. And then we determined what is the probability that when we stop, we're actually in this state as opposed to this state. In question 3, I'm going to start again at state 2. And we're going to go until we hit state 1. Along the way, I want to find the expected number of visits to or hits on state 5. So what is the expected number of visits to state 5? First up, we have to set up some notation. I am going to let Wij be the mean. I'm going to let Wij be the mean or expected number of visits to state J starting at I and stopping at K. And so what we want to solve for is we want W251. In what I'm about to do, we're going to keep restarting the chain from different places. So this 2 is going to be changing, but we're always going to stop at 1 and we're always going to be counting 5. So you might call this W2 alone. I think I'm going to leave all the subscripts there just for this first time through, but it is going to be very repetitive. I'm going to be dragging a lot of subscripts around that I don't really need to drag around. Yeah, but I think I'm going to do it just this one time. Sometimes I actually use just the first two for reasons, and I'll get back to that after this example. So whatever, I'm going to use all of them for now, but you're going to see very quickly that I don't need all of these subscripts. Okay, let me get that matrix back. What is W251 in a first step analysis? This means I'm starting at 2, I'm going until I hit 1, and I want to count the number of hits on state 5. So we're back sort of counting steps, and you might think you need a 1 plus here. But in question 1, we were just counting the number of steps it took starting at 2 to get to 1. So we cared about each and every step. But here we're going to start at 2 and go to 1, and we only care about the steps where we hit 5. And not in this matrix because there's a 0 here, but it may be possible to go from 2 directly to 1 and never hit 5, or to go from 2 somewhere else on a path to 1 and never hit 5. So there's no 1 plus in this equation. Okay, I'm going to look at the 2 row of the matrix. With probability 0.1, I'm going to go back to 2. So with probability 0.1, I now want to say starting at 2 and going until I hit 1, what's the number of visits to state 5? So that's W251, starting at 2, counting hits on 5, stopping at 1. With probability 0.5, I go to state 3. So now I want to say starting at 3, what's the number of hits on 5, stopping at 1. With probability 0.1, I go from 2 to 4. So I'll put a 0.1, and now I want to say starting at 4, I want to count the number of hits on 5 before stopping at state 1. And with probability 0.3, I go from 2 to 5. So I'll get a 0.3. And now I want to say starting at 5, what is the number of hits on 5 when I stop at 1? Now I have a hit on 5, but I'm not going to count that here yet, because just like we've done before, I now need to come up with equations for all these other variables. And when we work on this one, we're going to have a 1 plus in there. We're going to already have a hit on 5. You'll see what I mean in just a few moments. Okay, so to make some room here, I'm going to sort of get rid of the top of this matrix. Okay, I am going to write out, I need an equation for W351. W351. Starting at 3, I want to count the number of hits on 5 when my stopping criterion is I hit state 1. So I'm looking at the 3 row of the matrix. With probability 0.4, I have hit state 1. That's the 1 column. And that means I have 0 hits on state 5. It's over. I hit state 1, the chain has stopped. With probability 0.4, I go from 3 to 2, and now I want to start at 2, count the number of hits on 5 before I stop at 1. And with probability 0.2, I go to 5. So with probability 0.2, I'm starting at 5, counting the number of hits on 5, and stopping at 1. So you could see what I mean before when I said you don't need all the subscripts, because every one of these W's is going to end with a 5-1. Just going to do it this first time so that you can decide that you don't need the subscripts, and make sure you know what you're doing. Because I think for the first time through, it's nice to be able to say starting at 2, hitting 5, ending at 1. But clearly we don't need to write that all the time. So now I'm going to come up with an equation for W451. W451. Let me get rid of this row. You are just in my way. Starting at state 4, how many hits do we have on state 5 on our way to stopping at state 1? I don't go directly to 1. I don't go directly to 2. With probability 0.7, I've gone to 3. And now Starting at 3, I want to count the hits on 5 when we stop at 1. With probability 0.2, I go back to 4. So I get a 0.2. And then starting at 4, I want to count the hits on 5, stopping at 1. And with probability 0.1, I go to 5. And so with probability 0.1, starting from 5, I want to count the number of hits on 5 before we stop at 1. And the next equation is a little bit different than the others. We want something for W551. This says starting at 5, I want to count the number of hits on 5 before the chain ultimately stops when it hits state 1. And we already have one. We're counting hits on 5. We've started at 5, so I get a 1 plus. In this 3 subscript notation, I'm going to get that whenever these first 2 indices are the same. Starting at 5, I'm counting the hits on 5 before I hit 1, and we already have one because we started at 5. Now with probability 0.6, we have gone to state 1 and it's over. We're going to count 0 more hits on 5. With probability 0.1, we're going to go from 5 to 2. And now starting at 2, I want to count the hits on 5 before stopping at 1. And with probability 0.3, we're going to go to 4. So I get 0.3. And then starting from 4, I want to count the hits on 5. And I want to stop at 1. I think we've done it. We have all our equations. So I solved this system of equations. I did my usual thing of making it into a matrix vector system. Here, I'll write this up really quickly, just in case people are having trouble with this. So I've got a vector W251, W351, W451, and W551. And all we care about is the first one. And I'm going to move everything to the left side of these equations, except for totally constant things, which means this vector is going to equal 0, 0, 0, 1. And when I move things over, I'll talk about the first one in detail and then not the rest. I've got 251 and I'm subtracting 0.1, 251. So I have 0.9 as my coefficient for W251. I've got W351, I've got 0.5 of those moving over to the left. So I have negative 0.5. I've got 0.1 W451 moving to the left, so negative 0.1. And I've got 0.3 as a coefficient for W551, moving it over to the left, negative 0.3. So I'm going to fill out the rest of the matrix. The next row is negative 0.4, 1, 0, negative 0.2. The next row is 0, negative 0.7, 0.8, negative 0.1, and the final row is negative 0.1, 0, negative 0.3, and 1. So I inverted the matrix and multiplied it to the other side, to the left of that column vector, and I got that W251 is approximately 0.832. So this is a number of hits on state 5. And, it's fractional and that's okay. It's an expected number. It's an average. I got W351 is approximately 0.590. W451 is approximately 0.677. And W551 is approximately 1.286. This is what we were looking for. And this is the answer to question 3. As with question 1, we could show this formally by doing a conditioning argument. It's going to be pretty messy. We've got a lot of stuff going on here, but we could do it. And again, you do not need to drag those second subscripts through because there's a 5-1 on every one of these. However, if you were to compute this again, let's see, we're starting at 2 and we're stopping at 1. And in question 1, we determined that, excuse the scroll, that is going to take on average, it's going to take on average 4.376 steps if you start at 2 and stop when you hit 1. along the way, we could count hits on 2, 3, 4, and 5. We can't really count hits on 1. There's only going to be 1 hit on 1 because we're stopping. So this 4.376, let me bring that down here. Again, this is from question 1. This is starting at 2, the expected number of steps it takes to hit state 1. This is going to actually equal W221 plus W231 plus W241 plus W251. Now we've computed this, but we haven't computed any of the others. That's going to require a whole new system of equations. So that would be a little long to check out. But this is the expected number of steps it takes to get from 2 to 1. Along the way, you're going to visit state 2 some number of times, state 3 some number of times, state 4 some number of times, and state 5 some number of times. And so if you actually went through all the work of computing these, those should add up to be 4.376, and all is right with the world. Okay, I have one more question I want to do. These are all first step analysis questions, and although I will give you exercises that fall into one of these 4 categories, you should be able to apply this to problems that are slightly different. You'll notice that I didn't, in every other question, I said, oh, note that U1 is 0, and note that P1 is 1, and we had some kind of, values that were locked in. If I want to count, I never used those values in the right-hand side of my equations. I put in zeros and I put in ones when appropriate. And in the next question, I think that's really what you want to do. I'll show you what I mean. Question 4. It's going to be very similar to question 3. In fact, I'm going to go copy and paste it and change just one thing. So before we have, if the chain starts in state 2 and goes until state 1, what is the expected number of visits to state 5? Question 4 is going to be, we start at 2 and go until we return to state 2. In all of the other problems, we defined the stopping time for our searches as something that could happen at time 0. Like how many steps do you have to take to reach or hit state 1? If you start in state 1, you've taken 0 steps. Here, we have to allow ourselves to leave state 2 one time. So if I let W like 252 be starting at 2, the mean or expected number of visits to 5 before hitting 2, then that's going to be 0 because we've hit it at the beginning. So this is going to be before returning to 2. And if I want to use this kind of notation, I definitely need to put zeros in the right-hand side of the equation whenever appropriate, because I want to find this W252, and I'm allowing only 1 departure from 2. So I don't want to define this to be 0 because I want to find what this actually is. And I can't use it on the right-hand side of my equations because once I hit 2, I definitely want 0 steps. I don't know if that makes sense. So before I would have said that this is equal to 0, but now we're doing the return. And so my point is that I'm not using this on both the left and right side of the equations. Every time I've written my equations, I've put in zeros and ones where appropriate. And I always said, oh, but you could have put P1 there, or you could have put U2 there. In this question, I'm definitely going to put my zeros in and not try to use notation. So again, starting at 2, stopping at 2, how many times do I hit 5? That would be 0. Starting at 2, allowing myself 1 step away, and returning to 2, how many times do I hit 5? That is something else. That's not necessarily 0. Let's find it. I'm going to grab my matrix. And let's do it. W252. Starting at 2, going until I return to 2, so allowing myself to move away from 2. How many times do we hit 5? I'm going to look at my 2 row. With probability 0, I go to 1, so I don't need to write anything there. With probability 0.1, I've moved from 2 to 2, and it is over. So 0 steps. With probability 0.5, I've moved from 2 to 3. And now, starting at 3, I want to count the number of hits on 5 before I return to 2. So this 2 is kind of read as, okay, I'm starting at 3. I want to count the hits on 5 before I first hit 2. We just wanted to allow ourselves to move away from 2 one time, but once we're away from 2, all I care about is the first hit on 2. With probability 0.1, I'm now at 4, and I want to count the number of hits on 5 before the first time I hit 2. And with probability 0.3, we're at 5, and I want to count the hits on 5 before I hit 2. So I didn't say hit back here. I said return. Otherwise, I wouldn't have been able to leave 2 in the first place. So maybe I should use totally different variables here, but I don't know. I didn't think we needed more variables. There's a lot of variables. So I need W352. Starting at 3, I want to count the hits on 2 before I first hit state 2. The only time I didn't say first hit state 2 was when I started at 2, because I wanted to allow myself to step away from 2 one time. Okay, I'm going to look at the 3 row. With probability 0.4, I go to 1. And now starting at 1, I want to count the hits on 5 before I hit 2. With probability 0.4, I've hit 2, and it is over. I'm not counting any hits on 5. With probability 0.2, I'm going to 5. And now starting from 5, I want to count the hits on 5 before stopping at 2. And I'm going to need W452. So starting at 4, with probability 0.7, I'm going to be at 3, counting hits on 5 before I hit 2. With probability 0.2, I'm going to be at 4, counting hits on 5 before I hit 2. With probability 0.1, I'm going to be at 5, counting hits on 5 before I hit 2. I need an expression for W552. Starting at 5, going until I hit 2. How many times do I hit 5? I need to count 1 hit because there's already 1 there. With probability 0.6, I'm now going to start at 1, counting hits on 5 before I hit 2. With probability 0.1, I am going to be at 2. So now I'm going to start at 2, counting hits on 5. Oh, it's over. I hit 2. So that should be a 0. With probability 0.3, we're at state 4. So starting at 4, I want to count the hits on 5 before hitting 2. And I think I need another equation here. And yeah, I've got this W152 in here, and we haven't written that one out yet. So W152, I'm going to look at the 1 row of the matrix. With probability 0.3, I've gone from 1 to 1. And so now I just want to say, starting with 1, what are the number of hits on 5 before ending at 2? With probability 0.2, starting at 1, I've gone to 2, and it's all over. There's no hits on 5. With probability 0.1, I've gone to 4. So now starting at 4, I want to count the hits on 5 before stopping at 2. And finally, with probability 0.4, I've gone from 1 to 5. So I want to start counting the hits on 5 from there. So I get 0.4 W552. And I have a system of equations to solve. And it is what it is. I'm not going to solve this one. So there's the setup, but do not solve. So this was just like question 3, but I needed to allow myself to leave the initial state one time and one time only. And so you have to be a little bit careful, but it's really the same thing. So I hope you enjoyed that. I know I really did. I think first step analysis is so powerful. It allows you to answer some pretty otherwise seemingly complicated questions pretty easily. And we're going to do more of that next time on Markov processes.
Hi, Ozzy. Hi, Oz. You like your new friend Felix? You like your new friend Felix? Yeah? Okay.